Last lecture, we discussed Taylor's series expansion of complex functions. In this lecture, we will uh, develop a more general series expansion for complex functions. This general expression, this more general expression, is called Laurent's expression. Laurent series, this expansion, Laurent series expansion of complex functions is more general than Taylor's series expansion. Uh, in what sense it is more general? Let us see that. But before that, let us try to develop a momentum for this. It's understanding why Lawrence series, where it is needed. Now, we have here, say for example, we have this a complex plane, and we will be talking about as usual about complex plane. Lawrence, just 1 minute. Lawrence series expansion. Now this complex plane, in this complex plane we have, suppose this function, we have a function fz is equal to 1 by say z minus 2 into z minus 3, for example, as an example. Now obviously this function has these zeros, these singularities, one at z equal to 2, another at z equal to 3. If you go to complex plane, the situation is this: 1, 2, this is 2, then 3. Or let me keep it a little away from this. Let me show it 4. Z minus 4. This is 4. Okay. I want a series expansion of this. Series expansion of fz in terms of z equal to 0. About z is equal to 0. Now this is z is equal to 0 here. This is our center of expansion. Now the question is, the first singularity, the nearest singularity to this center of expansion is this. This is the nearest singularity, and distance between center of expansion and this first singularity, that is called radius of convergence. This is the center of this expansion. That means we want to expand this series about z is equal to 0. About z is equal to 0 means that you want this type of series, say c1 z1 c2 z2 z square plus c3 z cube plus dash dash dash. You don't want something like this: c1 z minus a plus c2 z minus a square plus dash dash dash. This would be an expansion about a at different point. A could have been, for example, as somewhere here or somewhere at some other location. We just want this type of expansion. This is called expansion about origin, or z equal to a, z equal to 0. Sorry, z equal to 0. Okay. Now the you can have Taylor series expansion about a point, provided you ensure one thing, that is there should be some neighborhood, however small they may be, but there should be some neighborhood about that point, that center of expansion, in which your fz should be analytic. And thank God we have it here. There is enough distance between this point, the center of expansion, and the first singularity. So there is a lot of area this of this circle, that is there, this disk, we say this area is it's the area in which our function is completely analytic. It is analytic, and hence we can expand it in terms of this Taylor's expansion. We can expand it about z equal to 0. Okay. Now suppose this now this area, this region beyond this singularity, that is inaccessible to our fz. Our fz cannot be expanded in that area. Now it is here that our yes, just one more thing, that is our second singularity was at this point. Taylor's expansion is applicable only in this region, in this, that is the world of Taylor's expansion. What about this Taylor's expansion? No. About z equals 0? No. Then there is another series expansion called Laurent series expansion, which takes care of these annular regions. Annular means a region that lies between two closed paths. So this region is, let me show it by dots. This is the annular region here. Okay. Now our Laurent series that will apply to this annular region. How and what does that mean? Let's see. Let's proceed now to this. Suppose there is one more thing that I should mention. Actually, there are three regions. One region is this which constitutes where we applied our Taylor series expansion. Another region is this annulus. Now, then third region is beyond this, up to infinity. The range of our Taylor series, this expansion, that is only this, and rest of it is taken care by Laurent. In fact, Laurent series takes care of this region as well, because as you will find, Taylor series expansion is a special case of Laurent series expansion. With this introduction, let us go to see why from does this Laurent series come. It comes simply from this Cauchy's integral formula. Both in generalized, we use generalized form, as well as we use that simple form. So students are advised to keep those two formulas right in your hand or before your eyes. So our situation is this. This is our situation. We have as closed path C1. Let me not name it C1. Then we have another closed path C2. Let me call this CO, outer closed path, and this, sorry, C1, inner closed path, CI. Now, COCI. Let both be centered. They are concentric, and both are centered at A. Okay. Now, this is the region. This annular region is the region where I am showing these dots. This is the region where our function is analytical. It can be analytical even here or there, but that is not the requirement. It may be. No, there is no bar on that. Now, let's consider this portion. I want to, since it is analytical here, I want to apply a Cauchy's integral formula to it there. For Cauchy's integral formula, we need an analytical region, a region where your function is this analytical. Let our function be abstract. Name of that function is abstract. According to Cauchy's formula, but I cannot have, I have one problem here. That is, this region is not bound by one single continuous curve. It is bounded by two curves. And this bounding by two curves is not what is needed for Cauchy's integral formula. We need a single continuous curve, because if we take this curve and this curve, these two curves, this curve will not only enclose this, it will enclose this curve will not enclose this, it will enclose this region. So I will construct a new closed path from these two, and that we have done at several occasions. Now the situation is this. You place a cut here, say, suppose we place a cut here. So it is like this, it will be, we will have to draw it. It is like this, and then this, then this, then this. This gap is only for convenience. Otherwise, these two are just coincident. They are coincident, and then this is C. Let me call this now C1. This is my closed path now. It has four parts. One is C1, starting from this, to this, and this is up to this. Let me say from A to C1 to B, and it is in the anti-clockwise direction. And then from B to this, B to C, let me call it C3. This will be C2, C3, and then C4, C4. Now I can apply this Cauchy's integral formula to fz in this region. And this will be Cauchy integral formula. According to Cauchy integral formula, fz will be equal to 1 by 2 pi I integral, loop integral of, now we have actually this continuous curve that we have now, closed continuous curve. This continuous curve has now 4 parts. Fortunately, 2 parts, integral along this path and integral along this path, these two will cancel out. When they cancel out, we will leave them. So we will have only an integral about path C1 plus C1 plus C3. Okay, C1 plus C3, and we have f gamma. Gamma is the variable of integration. Gamma minus A, and gamma minus z into d gamma. Okay, that is the Cauchy's integral formula. But we have not yet fully evaluated it, because we have just we have two curves, C1 and C2. So we break this into 2 parts. That is, fz will be equal to 1 by 2 pi I, that is common, and then we have integral C1 f gamma d gamma divided by gamma minus z, plus integral C3 f gamma d gamma divided by gamma minus z. Let me first evaluate this integral. Let me call it I1, and then let me call this I2. I1, I2. I1, I3, sorry. This is C3. So it is I1, I3. C1. This is I1, I3. Okay. To calculate I1, I will go to next page. Now, to calculate I1, I will keep this 1 by 2 pi I here, and I go there with this. I1 will be equal to I1. In fact, I have to include, to be frank, I have to include this 1 by 2 pi I. 1 by 2 pi I. 1 by 2 pi I. Okay. Then I have integral f gamma d gamma, gamma minus z, f gamma, this is C1 along path C1, f gamma d gamma, gamma minus z. Now, to evaluate this, the situation is here. This is C1, this is C1, and this A here. Our region of interest is this, and our point Z lies exactly in this region. Okay. Now, see, this is Z. Z is a variable point in this region. Now, this is Z, and this is A. And what is gamma? Gamma is variable of integration. That means gamma, you can think of gamma as gamma is the coordinate of this points on this path C1. So gamma represents coordinates of points on C1. Now, it was actually like this. Sorry for this. Okay. Now, so remember this, that gamma is on this path. Why? Because actually, what is this? This is line integral. And you know how line integrals are actually evaluated. In line integrals are evaluated by imagining the line to be divided into infinitesimally small elements. Each element is this d gamma. And f gamma is simply value of the function on this. Now, having said this, now see, so there is one more thing now, that is we will utilize a property of a geometric series that I have already actually discussed in my last video. I have discussed that geometry, and I'm going to utilize that here. We know that. Let me remind you what I am talking about. That is 1 by 1 minus x is always equal to 1 plus x square dash 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 to infinity. That means sum of this geometric series is this, provided the big condition provided otherwise not, mod x is less than 1. That means x should be a fraction less than 1. Okay, that this is the condition. Now we will take advantage of this and see what I am going to do here. See, you see, gamma is on this path c1 and z is here. So gamma is greater than z. This means gamma minus a, mod of gamma minus a is greater than mod of z minus a. Well, that's okay. So simple. Now, if that is the case, then ratio of, since this is bigger, this is smaller, I can make a ratio of this smaller divided by the bigger, gamma minus a, that will be this number. This quantity will be less than 1. At least its modulus will be less than 1. Okay. Now, we cannot compare complex numbers. They don't have ordering. So we have to resort to this modulus. Now, you have constructed something z minus a divided by gamma minus a number that is less than a quantity that is less than 1. So this quantity I will incorporate into it. This how I will write 1 by gamma minus z is equal to 1 by gamma minus a into 1 by 1 minus this 1 minus, now 1 minus this z minus a divided by gamma minus a. Now you can multiply it. First let us do it. Gamma minus a into 1 minus z minus a divided by gamma minus a. That is simply equal to, multiply this by this, gamma minus a into, when you multiply this by this, you get z, gamma minus a into 1 gamma minus a into gamma minus a. That cancels. You get minus z plus a. That is minus, this cancels, gamma minus z. So it is gamma minus z. Okay. Now we have established this, and then we have now 1 divided by 1 minus x, and that is equal to 1 by gamma minus a into, now this remain. Now the question of this one just a minute. So 1 minus x minus this. So we have 1 plus, first term is 1 plus x, that means this z minus a divided by gamma minus a. Second term, it is square, that is z minus a divided by gamma minus a whole square, plus, you know what is there. So having done this, now I will do one more thing, that is I will write it as it is, 1 by gamma minus a and then write this as a series. Say we have, say I will write them as this z minus a. There is z minus a everywhere, gamma minus a everywhere. You will say no sir, there is none here, but you can imagine one here. You can say there is z minus a raised to 0, gamma minus a raised to 0. So I will write z minus a divided by gamma minus a whole raised to n, when n starts from 0 and goes to infinity. n starts from 0 and goes to infinity. You know this series converges. Okay. With this thing, I will now substitute this quantity in place of this here. So I will have this result that I am going to write on the other page. That is what it was. I did not actually. It was fz is equal to, no, fz is not this. This is only one part of fz, I1. So I1 is equal to 1 by 2 pi. Then this I1 is equal to 1 by 2 pi I, 2 pi I. Then we have integral, uh, that is f gamma d gamma, f gamma d gamma, f gamma d gamma divided by gamma minus a, gamma minus a, gamma minus z, gamma minus z, gamma minus z, and we have established that 1 by gamma minus z is equal to 1 by gamma minus a into this 1 by gamma minus a into this summation of this n equals 0 to this n equals 0 to infinity z minus a divided by gamma minus a whole raised to n. Substitute now this here in this formula. I have I1 is equal to 1 by 2 pi I integral C1. Now integral f gamma in this integral, and then f gamma d gamma divided by gamma minus z into this quantity, that is this n equal to 0 to infinity z minus a divided by gamma minus a raised to n. Okay. Now out of this I will take z minus a. See, it is n equal to 0, n equal to 1 raised to n. Of course, I will take this factor to one side, and I will do one more thing. That is, I will write it here. That means I can take this summation out of this integral. I will assume that in fact these things have actually been established, and it takes a lot of effort if we just stop it here and try to explain this. These things can be postponed, and these are not actually a part of our syllabus, but these should not be taken for granted. You take it out, no, mathematicians will not like this. They won't permit it unless they establish it. Okay, these things have been established at other places, so we will assume that it is there. So I can take it out, and I will write simply I1 is equal to 1 by 2 pi I, then summation n equal to 0 to infinity, then integral, then I have this situation. It is better to bring this here. Yes, I will do one thing. I will take this out, n equals 0 to infinity, and then what I do, I enclose some things in brackets. You will see why. I will write 1 by 2 pi I into then I have this 1 by 2 pi I and integral f gamma d gamma minus. Now here is the situation. We have gamma minus z here. Oh, it should be sorry, we have done something somewhere weird. Yes, of course, 1 by gamma minus z we had actually 1 by gamma minus z. In that place we had this quantity 1 by gamma minus a into this. So what I have done here, I have substituted this much, but not this much. It was, we had to write here gamma minus a in place of 1 by, I once again repeat, in place of 1 by gamma minus z, I had to write 1 by gamma minus a into this. I had written this gamma minus z as side, but this part I had written here, but not this part. This gamma minus a into this. So it is f gamma d gamma divided by, now c, it is gamma minus a, this is gamma minus a raised to n, so it will be gamma minus a whole raised to n plus 1. Okay, into. Now, now remains z minus a whole raised to n. Okay, this quantity that is within the brackets, this quantity, I will write this whole quantity Cn. I will write Cn. Let Cn equal to 1 by 2 pi I integral f gamma d gamma divided by gamma minus a raised to n plus 1 into, no, not into, this. When you replace this whole thing by Cn, it simplifies down to this. It becomes I1 is equal to, in this integral, n equal to 0 to infinity Cn into, we had this much. See, in this whole place I have Cn, and then I have z minus a raised to n. Z minus a, sorry, z minus a raised to n. Oh, sorry. Now z minus a raised to n. So just 1 minute. Just 1 minute. Z minus a raised to n. This is here. Yes. Then we go to this z minus a raised to n. Add z minus a raised to n. Once again, for your this satisfaction, see, it is in this place I have written this Cn, and rest is z minus a raised to n. So good. That is it. I1. Then after I1, let's now calculate I2. I2 similarly will be equal to, let me see what I2 was. I2 was this, this was, it was basically I3. I3 was this C3 F gamma D gamma gamma minus Z C3. C3 is this. So it is I3 is integral C3 F gamma D gamma gamma minus Z. Now see, we now have this part of the curve, this part is now C3 part, and now gamma will be here. So the point gamma is always a point on the curve, so gamma will be here on this. Z, as usual, you know, Z will be there. Why not here? Because we have not assumed this function to be analytic here. We have assumed this function to be analytic in this region. So our Z, we have to take that point here. Now, you have Z here, gamma here. Now you can better see. This is a center of the two. These you can better yourself see. Now the tide has turned. That means Z is greater than, mod Z is greater than mod gamma. You can see. You can check yourself. Now, because gamma is on this curve, so Z is there in the region, so naturally it is greater than this. So now we have to write Z minus A is greater than gamma minus A. Say gamma minus A. So we have one thing, that is, if we now divide Z minus A divided by gamma minus A, as we did in our previous, we will get a number greater than 1, and that will not make our geometric series convergent. So we have to take this gamma minus A divided by Z minus A. Z minus A. This will be less than 1. This will be less than 1 now. Now, so that is the difference. Previously, it was Z minus A divided by gamma minus A less than 1. Now it is gamma minus A divided by Z minus A less than 1. Now expand this in this powers. So we will have to write 1 by gamma minus Z is equal to, as usual, we did it in previous this example. We will write 1 divided by C. We will write 1 divided by, here we will write Z minus A, as we did in previous case, gamma minus A into 1 divided by, you have gamma minus A, 1 minus gamma minus A divided by Z minus A. Let's check whether it is equal or not. Let's check, but I don't have space here. So let me write it here. Yes, I can write it here. So it will be Z minus A into 1, that is Z minus A into Z minus A into this. So it will be minus Z minus A will cancel. We'll get gamma minus A, gamma plus A plus A. So I will get A cancel. Z minus gamma. I get reverse of this. I wanted gamma minus Z, but I get Z minus gamma. And that we can adjust by this minus 1. We can write it minus 1. Okay, clear? I think it is clear now. Now, this ratio is less than 1. So I can use this geometric series for expansion of this. And when I do that, here is the result. Sorry. 1 by gamma minus Z, 1 by gamma minus 1 by, it is I3, 1 by gamma minus Z, okay, into it was, no, 1 by, we have not yet substituted, 1 by gamma minus Z is equal to minus 1 by Z minus gamma into 1 divided by gamma, this Z minus gamma here, and gamma minus, I have Z minus gamma here. No, wrong. No, it is wrong. I am doing something wrong there. Now I have, this is C1. Okay, C1 is okay. This is C3. See, it is 1 minus gamma minus Z minus 1 by Z minus A, then divided by 1 minus gamma minus A divided by, let me write, just a minute, let me write it on a page of paper. It actually will make me, otherwise I will have to turn these pages. 1 by gamma minus Z is equal to minus 1 by Z minus A into 1 by 1 minus gamma minus A divided by Z minus A. So I go back and write this there and simplify it. I have this situation. Now I have minus 1 by Z minus A, it is Z minus A into 1 by 1 divided by 1 minus 1 minus gamma minus A divided by Z minus A. So if I multiply, yes, we have already tested that. Now this is my geometric series. I have to write in its place 1 plus x square plus dash, while x is this. So I have 1 by gamma minus Z is equal to minus 1 by Z minus A into now this. It will be 1 plus, sorry, I will write this 1 plus x is gamma minus A divided by Z minus A plus x square, Z minus A is just gamma minus A divided by Z minus A square plus x cube gamma minus A divided by Z minus A cube plus dash 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 dash. Okay, that you know, we can write 1 by Z minus A into, this can be written as power series. This, yes, of course, we can write it as n equal to 0 to infinity, as we did in the previous case. It is inside we have this, we have gamma minus A divided by Z minus A raised to n. So that is our this value of 1 by gamma minus Z. Now I am now going to substitute this in I3. Now what was that I3? Have a look at that. You have I3, not this actually. So we have I3 somewhere here. I3 is this integral f gamma d gamma divided by gamma minus Z. So C3 f gamma d gamma divided by gamma minus Z. So I will write it here. First I will write it here. So I have I3 is equal to 1 by, first you have 1 by 2 pi I. For your satisfaction, let's go back and see 1 by 2 pi I is here. This is common to this and this. So we will write first that factor, then other factors, then I3 1 by 2 pi I, then integral f gamma d gamma divided by gamma minus gamma minus Z. Z is gamma minus Z. So I have to substitute this here in place of this gamma minus Z. I will write I will write it on next page because I don't have any space available here. So I will have to use this or let me try to write it here, accommodate it here. I3 is equal to 1 by 2 pi I, 2 pi I. Then I have this, and there I have this ab gamma d gamma, ab gamma d gamma. Then I have gamma minus z, gamma minus z. Okay, no 1 by gamma minus z. In that place you have to ab gamma d gamma. You have to write in place of gamma minus z, 1 by gamma minus z. You have to write minus 1 divided by z minus a. Okay, then this n equal to 0 to infinity, and then gamma minus a divided by z minus a raised to n. Okay, now I will go to next page, and I will once again write it first on this piece of paper. Then I have y3 equal to, now I3 is equal to 1 by 2 pi I. Then I have integral f gamma d gamma into minus 1 by z minus a into, then n equal to 0 to infinity. I have gamma minus a divided by z minus a whole raised to n. Okay, now for me it will become easier. I have I3 now. I3 equal to, I will write it here, I3 equal to 1 by 2 pi I, 2 pi. I can take this minus out. This minus that I have here, I have in one of the factors. Just see it. I have minus here in one of the factors. You can take it out. That is better. Minus 1 by 2 pi I. Then I have integral. Then I have f gamma d gamma. Then I have this z minus a. This z minus a. I have z minus a raised to n plus 1. N plus 1. And then I have next I have this I have this series, this sorry, first of all I will take this, first I have to take this out, and then I can do this. First let me keep it like this, 1 by z minus a. Then I have ahead of that I have this summation n equal to 0 to infinity, and then gamma minus a divided by z minus a whole raised to n. You may have a look at this once again. This is what I have written in there. This minus I have taken out, then 1 by 2 pi I, then f gamma d gamma, then this. This z minus a, I have kept it this here separate. First I try to combine it with this, but then I realized that first I have to take this out, then I can do this. Now, you will take this summation out. Okay, if you take this summation out, then this summation out, taking the summation out as we did in previous case, I3 is equal to this sigma n equal to 0 to infinity. Then we have this bracket here, 1 minus 2 pi I, then integral, then f gamma d gamma divided by, now I can combine this, z minus a raised to n plus 1, n plus 1. Then I have gamma minus a, or I can do one thing. Yes, it is z minus a raised to n plus 1. I can do one thing. Instead of writing z minus a raised to n plus 1, I can write z minus a raised to minus n minus 1. That is one and the same thing. So I can write that I have this minus 1 minus n. Yes, or keep it like that. Keep it like that. Then I have gamma minus a whole raised to n. Very good. Now this gamma minus a whole raised to n, this two I will actually keep this with this whole thing, this gamma minus a, but the variable z, that I won't let there. I will write it outside. 1 by, what was it? You have here z minus a raised to 1 by z minus a raised to n plus 1. n plus 1. This is our this C2 Cn, sorry, Cn. But there is one problem. This is the same formula as for previous Cn, but with minus sign. This has a minus sign. So we will have to wait a little bit before we can do anything to it. We will have to wait a little bit. We can absorb. This is C3. Now there is one more thing that how I can absorb it. I will tell you. So far as this minus is concerned, let me reverse the this traversal of C3. Instead of going in that direction in which I am going right now, I will go in opposite direction. That will generate a minus. That minus with this will combine and give a plus. This means that I can write I3 is equal to sigma n equal to 0 to infinity. Then I can write this thing minus 1 by 2 pi I into this much minus integral minus C3. Instead of C3, I write minus C3. That means in opposite order. You are traversing it in opposite order. F gamma d gamma into one more thing, that is gamma minus A into gamma minus A raised to n, and this I close, and then I will lift it up z minus A and write minus 1 minus n minus 1. This was n plus 1 here, n plus 1 here. I have taken it to numerator where it is minus n minus 1. So this minus and this minus will go. I have I3 equal to n equal to 0 to infinity, then 1 by 2 pi I integral, sorry, this, oh yes, integral, it is integral here, integral is integral C3, this C3 minus C3 F gamma d gamma into gamma minus A raised to n into z minus A raised to minus n minus 1. Now, I will now change indices. I can do it. Suppose you have, for example, you have something like this: x minus a raised to m n is equal to y minus y minus t raised to n plus 1. For example, if this is true for this index m, we can by changing the name of the index. Say suppose x minus a. Now I change the index symbol of the index. I will not represent it by n. I will represent it by say x. Say t, for example, t. The equation, sorry, this is t here. So I will represent it by say m. It's y plus t raised to m plus 1. This is as true as this. No problem at all. You can change these indices. You can change the, I mean, not change like that. It means that you can use any symbol, any letter for them. So what I am going to do, that is you will see what I am going to do. I will simply now change the index here. Just a minute. I will change this index in such a way that I will get the desired result. What is that such a way that gives me desired result? I will tell you. First of all, we have to bring this back, bring that equation here. Again, this is the problem in this screen recording. I3 is equal to, this is our I3. I3 is equal to, I have I3 is equal to, then I have this once again, this is problematic, so I will write it on this. I3 is equal to this n equal to 0 to infinity, and then I write 1 by 2 pi I integral minus C3 f gamma d gamma into n gamma minus a raised to n into z minus a raised to minus n minus 1. Okay, minus n minus 1. Okay, now I will use this and write it here. Now I have this uh, on this page I3 equal to n equal to 0, n equal to infinity, 1 by 2 pi I, 1 by 2 pi I, integral f minus c3 f gamma d gamma into gamma minus a whole raised to n. Okay, then I have this this whole thing in bracket, and next I have z minus a raised to minus n minus 1, minus n minus 1. Okay, now I am going to change this this index. I am going to change that. How? What I am going to do? I will tell you what I am going to do. I will, in place of this minus n minus 1, I will replace this minus n minus 1. Let me put, I will make a substitution. Let m equal to n plus 1. N plus 1. Okay. If n is equal to m plus 1, that means therefore minus m is equal to minus n minus 1. Right? That is okay. Now we have this thing, then I can substitute minus n here. Okay, then I have n here, that n will become this, from this substitution n will be equal to m minus 1. This 1 will go to this side, so that will be m. So I will substitute in place of m m minus 1. And where else do I have it? Yes, here. When n is equal to 0, see, when n is equal to 0, m is equal to what? M is equal to m at that time is 0 plus 1, that is 1. And when m is equal to n is equal to infinity, m is equal to that too will be infinity. But this is not my substitution. This is not the substitution that I require. I require this substitution. See, I will have this substitution, not this substitution. This will prove up no value for simplification of this. I will do one thing, that is, if I put this, say, n equal to, let us try this thing, then I have, say, suppose I have n equal to m. What should it be? I need first, I want to convert it into this. If I put my m is equal to minus n minus 1, if I do that, m, okay, then I can write it as, if n is equal to 0, m is equal to minus 1, n is equal to infinity, m is equal to minus infinity, 0 to minus infinity. Yes, yes, let me do it. Let me try it. I think this is correct. Now, you have m is equal to minus n minus 1. This means that n plus m plus n will be equal to minus 1, or n will be equal to minus 1 minus m. Minus 1 minus m. Okay. Now, when m is equal to, when n is equal to 0, n equal to 0, m will be minus 1. M will be minus 1. Okay. Then when m is equal to 0, n is equal to minus 1, and then I have n is equal to infinity, n is equal to infinity, m will be equal to minus infinity. So situation will change here. After writing this, I have this situation. I3 will be equal to, now, in place of this n equal to 0, I will have now m equal to minus 1. Because when n is equal to 0, m is equal to minus 1. So minus 1. In place of this infinity, I will have minus infinity. Then I will have 1 by 2 pi I, correct? Then I have integral minus c3. This is orientation of this loop, it has nothing to do with this index. Now next I have ab gamma there, that is there, ab gamma d gamma. Let me first clear this space. D gamma, okay. Gamma minus a raised to n. Now n is equal to minus 1 minus m. You will write minus 1 minus m. That will bring it down, and it will be there. Gamma minus a raised to 1 plus m, or m plus 1. Then I have z minus a raised to m. Okay, z minus a raised to m. Right. Now, after having this index change, m is equal to this. Now see, this is the philosophy. Now this is true for index m. Suppose I had not used m. Suppose I had used L here. So it would have L here, L here. Okay. Suppose I had used K here. Then it would be K here, K here. This means that this equation is true for one index. This will be true for any index. We can bring back our n. It is as good as this m. So using this philosophy, then we have once again, I have to write it in a fresh, say I will write it here. I have this space here. So I3 will be equal to this. I will write back n is equal to minus 1. I think you understand this. It is simply that we can use any symbol for index. We can adjust indices in this way. It's a very useful method. M is equal to minus 1 minus infinity, and then I have 1 by 2 pi I, 2 pi I, and then I have f this gamma, f gamma d gamma, divided by gamma minus 1, gamma minus a raised to 1 plus m. 1 plus m is 1 plus n, or n plus 1. This close, and then we have z minus a. Z minus a was equal to, what was it? It was m. Yes, we can write n. Good. Now I will do this thing, that this enclosed, this now has the same shape as the previous. Which one? Let us see what was difference. None at all. You can go back to that Cn somewhere for that Cn. 1 by 2 pi I f gamma d gamma, gamma minus a raised to n plus 1. You have here n plus 1. This is n plus 1. Now back. You see f gamma d gamma, gamma minus a raised to 1 by 2 pi I. 1 by 2 pi I. F gamma d gamma, gamma minus a raised to, now this minus c3. See, c3 is, after all, it is a curve. So minus c3 is also a curve. Let us rename it. Let us name it c. So if c is, well, if c is this within c1 and c3, it is okay. No problem at all. So it is not necessary we will carry this burden of this with us. So it is, now we can write it Cn, simply Cn. Then we have this situation. We have got a simplified this integral, that is n is equal to minus 1. Simplified this expression Cn, then z minus a raised to n. Okay. N is equal to minus 1 to infinity, and then this. Now we have two these expressions, one for I1 and another for I2. Then fz will be equal to fz. Let us go back to that. Fz is equal to, where from did we start? This was quite a, see, fz is equal to this integral plus this integral. Both the values you have now calculated, then we will substitute them here. This is simply I1 plus I3. I1 is this, n equals 0, infinity, Cn z minus a raised to n. I1 is this 0 raised to this, n equals 0 to infinity, Cn z minus a raised to n. Now plus I have this now, n is equal to minus 1 infinity, Cn, z minus a raised to n. Okay, n here, n there. Okay, but see, we have now one interesting thing, that is we have this from 0 to, it is this thing, 0 to infinity, infinity, 0 to infinity, like this, and another from -1 to infinity. Since we are this n is integer, it is 1, 2, 3, 4. This means that this covers the whole range from minus infinity to plus infinity. So it covers the whole range from minus infinity to plus infinity. So we can absorb them in the same this group, and we can write there. We can write it like this. Yeah, or I have this space here. Fz is equal to Fz is equal to Fz is equal to n is equal to minus infinity to plus infinity, minus infinity, oh sorry, it is minus infinity to plus infinity, f cn z minus a raised to n. Once again I tell you that this is actually in this, sorry, go back to this. Basically, this n does not have non-integral value. It is integral value. This means that these two cover all the integrals from minus infinity to plus infinity. This is the expression for this, and see why it differs from Taylor's series expansion. There you start from 0 to infinity. Here you start from minus infinity to plus infinity. We will now uh, uh, discuss problems based on Taylor series and Laurent series. It has been a very long video, and a little bit this hard. Not that anything. I have tried my best not to leave anything to assumption or to this confusion at all. Rest. It all depends upon you, whether you did understand or not, or maybe I might not have been able to convey it in more in a better way. That is, let us leave with this impression that we have completed it, and completed it successfully without any confusion. Thank you so much.